Welcome. We have been looking at plotting the regular solution free energies. We plotted the ideal solution free energy, then we plotted the regular solution free energy with the regular solution parameter being positive. We plotted it for different temperatures. We defined normalized temperature, which was our normalized regular solution order parameter, which was normalized by RT. And so, this quantity which we called as alpha stands for inverse temperature. Alpha is omega by RT. So, you can think of this as a temperature which is normalized by omega by R, and this quantity we then used for different values. Then the smaller values correspond to higher temperatures and higher values correspond to lower temperatures. So, we saw that there is a critical point at the value of alpha equal to 2. Above that, which means below the temperature, the system phase separates, which means it develops two minima with a maxima in the middle, and the minima are symmetric and about 0.5, which is where the maxima exists. So, in this case then we can go and construct the phase diagram itself. So, the phase diagram construction given free energy is something like this. So, I have a free energy, right. So, the free energy is something like that. Then I need to draw a common tangent and then find out the points. So, this is at some temperature T1, and similarly at a temperature which is say higher than T1 and T2 is greater than T1. If T2 is higher, then these points are going to come closer. So, the curve looks something like that. Then you draw a common tangent again and then you get to the points. Okay. So, these points, then when you plot T versus x, and then there are these points which are at T1 and there are these points which are at T2. This is let's say T2. So, if you get all the points, then you get something like that. So, this is the miscibility gap where you have this two phase region. So, this is how we do the construction of the phase diagram given the free energy. Now, we have the free energy of mixing, which is a very symmetric, very nice curve. So, the free energy versus composition in this case looks like this, right. So, it is right, it is something like this. So, the common tangent is going to be like this, right. So, we want to find out. In other words, the minima for the curve and the common tangent point happens to be the same. So, in this case, if suppose there is a way to identify to the left of 0.5 and to the right of 0.5 where the minima point are, and it is symmetric about 0.5, we can check that it indeed is so. Then we can construct the phase diagram by taking this free energy versus composition curve at different temperatures. Okay. So, we know that the delta G is given by RT, because we normalized it, is given by alpha, which was nothing but omega by RT, right, x into 1 minus x plus x ln x plus 1 minus x ln 1 minus x. Okay. So, we know that when we are doing this kind of calculation for different x, you have to define x itself as a vector, and for that vector at different points you can calculate the delta G. So, x versus delta G then is useful in determining the free energy versus composition curve, which can then be used along with the minimization routine to obtain the phase diagram. Okay. So, the first thing that we are going to do, so we are going to construct the phase diagram for the regular solution free energy. The first thing that we are going to do is to define a free energy curve. So, let me call this as dG. Okay. This is a normalized dG, this is not the dG that we defined earlier. So, let me call this as dG and let me define a function. So, as usual we go to Octave and I generally invoke it from the terminal because it is better. So, desktop, okay. So, I am in that directory. So, I am going to say Octave. Okay. So, I have got octave window now. So, I am going to define a function, and the function definition is done as follows. Function, let us say y is equal to, what are the input values? G of a comma x, okay, where a stands for alpha, which is omega by r t. Okay. And how is the function defined? Y is equal to a dot star x dot star 1 dot minus x, right, a into x into 1 minus x, because that is alpha into x into 1 minus x, dot plus x dot star logarithm of x dot plus 1 dot minus x dot star logarithm of 1 dot minus x. It is a good idea to put a semicolon here, then say end function. Okay. So, we have defined the function, and you can define x as 0.001 and then let it increase. So, let us do it 0.001, let it increase by 0.001, 0.999. I am avoiding the values of 0 and 1 here. I am not going from 0, I am not going to 1. That is because these logarithmic expressions. So, if I put 0 here, then this is going to give up. If I am going to put 1 here, this is going to give up. So, when you have expressions like this, it is better to not go to 0 and 1, where it will give you a not a number error. So, that is why I am avoiding this. So, I defined x now, okay, and I am going to say that CLF, which is for clearing the figure. So, I have an empty figure, which is where all plotting will be done. So, I am going to start with a is equal to 1.0. Okay. So, first I start with a equal to 1.0, then I am going to, let me start with a of I. I am going to define a itself as a vector, because there are going to be several a values, because a corresponds to temperature, inverse of temperature. So, taking different a values means that I am looking at different temperatures. At those temperatures, I am trying to figure out how the phase diagram looks. Remember, the phase diagram construction means that the free energy has to be taken at different temperatures, and the minima points are to be identified at those temperatures. So, the identified minima points are to be plotted against the temperature, which means I need to do this computation at different temperatures. In our case, the temperature is in the parameter alpha. So, it is inverse of temperature. So, I am going to change the alpha, and because it is inverse of temperature, lower alpha means higher temperature and higher alpha means lower temperature. Okay. So, alpha is 0 is actually infinite temperature, and alpha infinity is actually 0 temperature. So, we are going to use this. So, I am going to define a of I as equal to 2.0. Okay. So, that is the a, sorry, a of 1 now is 0 is 2.0. Then I am going to say for I is equal to 1 to 400, what am I going to do? I am going to identify the minima. For that, there is a command called fmin bnd. So, this is find the minimum which is bound, and where is the minima? So, it has to be found in terms of, okay. So, I am going to define it in terms of ai. So, the current a. So, when I equal to 1, it will take a1, and I equal to 2, it will take the corresponding a2, which is a different temperature. So, it is going to take ai comma x comma, then it has to the fmin bound is going to find the minimum for the given function, that is for this function g, it is going to find the minima, but for that minima you have to say in which interval the minima lies. Okay. We know that there is a minima which lies to the left of 0.5 and another minima which lies to the right of 0.5. So, I am going to do this minimum calculation twice by giving these two bounds. I am going to avoid 0.5, because 0.5 is a point where there is an extrema. So, in order for the computation not to get into difficulty, so I am going to do 0.001 to 0.499. So, that is the one bound. within which it will try to locate a minima. And then there is a parameter for the system to do the optimization, which is known as tolerance of x. So, the tolerance of x I am going to give as 1 point e power minus 6 or 12. Okay. Now, this is very important. I have a video of mine for about 10-15 minutes trying to figure out what went wrong in one of my earlier recordings. What went wrong is that I also put a colon mark here. Okay. So, tolerance x is the parameter for which we are giving values. So, the value that follows this tolerance x separated by a comma should be just a number. Okay. So, there should be no quote marks on this. If you do give, then it gives some nonsensical results. So, this is very important. So, I have defined C. I also define a DFI, which is nothing but f min bound at x. So, this means that you have to find the minima for this function by varying x. For what value of x this function reaches minima. So, this is what this at of x means. So, G of a of I comma x, and this time we are going to look for a minima in the range 0.501 to 0.999. So, optim set I am going to give the same tolerance to which it will determine the minima, and that is 1 point e power minus 12. Okay. So, we have done this. Now, I have to change I plus 1 is equal to a I plus 0.01. Okay. So, the temperature or the alpha parameter is going to increase by 0.01. So, that is how the temperature is going to be reduced in the calculation. So, end for. Okay. So, this is because when I defined the function I also did not put the semicolon. So, it keeps doing this, which we can avoid if we do not put the semicolon. So, now I am going to want to plot the phase diagram, right. So, what is it that we have done? So, let us take a look at it. What I did is in the script, first I defined a function. What is the function that I defined? The delta G function I defined. Now, I took different alpha vary. What does that mean? Alpha is equal to omega by RT. So, varying alpha means temperature was varied. So, for this varied temperature, I found out where the minima points are. So, I have for every alpha, right, a corresponding composition. There are two compositions. There is one on the A rich side and there is another one on the B rich side. Okay. So, for every alpha like 2 or 2.01, 2.02, etc., I have identified what this composition is, what this composition is. So, we need to plot this. So, the composition will go here, the two compositions corresponding to the particular alpha value, but alpha is actually 1 by temperature. So, typical phase diagram is T versus x. So, if I want to plot, then I need to plot 1 by alpha. 1 by alpha is nothing but RT by omega. In other words, the y axis becomes a temperature which is normalized by omega by r. So, that is what this is going to be. So, I am going to do that exercise. So, I am going to say for I equal to 1 to 400, I am going to first take the B of I as nothing but A of I, okay, end for. So, I have now taken alpha into a variable called B. What I am now going to do is to plot. First, I am going to plot the curve on the left side 2.5. So, that minima was identified as C, comma 1 dot slash B. Okay. So, you have this curve, as you can see, it is a very nice curve. So, from 0 to 0.5, it has identified the minima points. Now, I have to plot the other half. So, I am going to say hold on, which means the next plot is going to be plotted on the same curve. So, I am going to say plot now D, which is the minimum points identified to the right of 0.5, I am going to say plot. So, now I have a full phase diagram. Okay. So, this again is something that you might have seen in a textbook like Gaskell. They give both these curves. See, remember the last part of this lecture we saw this kind of curves. What were the curves? The curves were like you have something like this, and then you have something that goes like that, and then you have something that goes like that, and then that you have something that it at different temperatures. So, it will go. So, when the minima point comes, so it will still start from here, and then it will go something like this, like that. Okay. So, these minima points keep shifting to the right and to the left towards the y axis. Okay. So, that is what we saw. So, it should be like this. Now, what we have done is to identify these points and then plot them, right. So, you will get T versus composition. So, that will be like that. So, these points actually correspond to these. Okay. So, that is how the phase diagram is identified. That is what we have obtained as the phase diagram for the regular solution free energy. Please remember, we have used minimization, that is because the delta G has that structure. So, the minimum point also happens to be the common tangent point. If it is not, then you have to actually do the proper minimization, but in this case because this works, we can use this and do this. So, the next thing to do, of course, this is the entire phase separation region in which we want to identify the spinodal region. The spinodal region is defined by the points at various temperatures where the second derivative with respect to composition becomes 0. So, we will do that and we will try to plot the same thing on this figure. So, that is the next part of the exercise. We will do it next. Thank you.